Welcome to the Deep Dive, where we take one fascinating topic and, just for you, we distill all the knowledge you need so you can grasp it quickly and thoroughly. It's all about hitting those aha moments without, getting bogged down.
Absolutely.
Now, you're approaching this with the discerning mind of a philosopher,
Right.
which is perfect, because today we're diving deep into the work of someone who truly revolutionized logic, George Boole.
Indeed, George Boole lived from 1815 to 1864, an English mathematician. He really changed the game when it comes to how we think about logical reasoning.
Yeah.
And it's interesting because he began as a schoolmaster and then rose to become a professor of mathematics at Queen's University in Cork. But his real lasting impact comes from his groundbreaking work applying this, at the time, kind of new field of symbolic algebra to the very core of logic.
Okay. So, when we think about the history of logic, Aristotle, right, and his system of syllogisms, that often comes to mind.
Right.
But Boole, he kind of blew that wide open, didn't he?
Yeah, he went beyond just a catalog of different argument forms. He created a general system, an algebraic language, if you will, that could handle much more complex arguments.
Right.
And the two major works that he's known for, the Mathematical Analysis of Logic from 1847 and the Laws of Thought from 1854, these were really the cornerstones of this whole shift. It's kind of like, if you think about it, Aristotle gave us this very detailed map of a small area, but Boole gave us the tools to map any logical terrain.
That's a really, really good analogy.
All right.
And what I find particularly interesting, thinking about it from a philosopher's point of view, is that Boole was already a respected mathematician before he even turned his attention to logic.
Yes.
Right, like he was deep into differential equations and the calculus of variations, published a ton on those subjects. So, this wasn't some logician dabbling in math. This was a serious math mind bringing all his tools to a new playing field.
Absolutely. It speaks to a very strong belief that logic itself could be tackled rigorously through mathematics.
Yeah, and, his background, it wasn't the typical, path of academic privilege or anything like that.
Oh,
It
yeah.
was his father clearly instilled this love of science and invention in him.
Yeah.
And through self-study, driven by access to books, in particular from Sir de Bromhead, he mastered multiple languages and really high-level math. It's like that self-driven curiosity. It seems essential to understanding his breakthroughs later on.
It really does. And all this early work in mathematics, it earned him some serious recognition. He was mentored by Duncan F. Gregory, who was the editor of the Cambridge Mathematical Journal, a pretty influential publication.
Right.
He formed strong bonds with people like Arthur Cayley, who was really impressed by his work on invariance, and of course Augustus Comorgan, who became his lifelong friend and kind of a friendly intellectual rival, you could say.
Yeah.
And receiving the Royal Society's Gold Medal in 1844 for his work on differential equations, that really solidified his status in the world of math.
Absolutely. So, he wasn't working in a vacuum, right? He was part of this very specific intellectual scene. So what was going on in 19th century English mathematics? What was the context that maybe set the stage for him to take this algebraic approach to logic?
Well, to really grasp what he was doing, you have to understand that the 19th century was a time when mathematicians, especially in England, were really wrestling with the fundamentals of algebra. Like, what are negative numbers? What are these imaginary numbers? What do they even mean? There were some heated debates.
Right.
So in this environment, the work of George Peacock, who distinguished between arithmetical algebra, which was all about positive numbers, and symbolical algebra, a more formal system with abstract rules that didn't depend on a specific interpretation, that was huge.
Okay.
He also came up with this principle of the permanence of equivalent forms. It basically said that rules that worked in one algebraic system should, if possible, carry over to others. And this push towards symbolical algebra, where the focus was on the formal rules, that was key for what Boole would do.
I see. So this trend towards symbolical algebra where the rules were king, that opened up a way of thinking that could go beyond just numbers and into areas like logic.
Exactly. And on top of that, mathematical techniques like the separation of symbols, which people like Servois and Gregory were using to solve differential equations, that was gaining traction.
Right.
That's where you treat mathematical operators as independent symbolic things. And then you have Boole's friend, Augustus de Morgan, doing this groundbreaking work on the foundations of algebra, and he was starting to see symbols not just as representing quantities, but also as representing operations themselves. This idea of symbols being active agents, like operators, that probably really resonated with Boole.
Right. Okay. So we've got this idea of manipulating symbols based on these abstract rules.
Yeah.
That was already a big deal in mathematics. Now, of course, we hear Boolean algebra all the time, right? It's almost like a synonym for the algebra of logic. But our sources point out this subtle but important difference.
Hmm.
What we call Boolean algebra today isn't exactly what Boole himself originally came up with.
Yeah, that's right. And it's important to be precise, especially for a philosopher. The term Boolean algebra actually came later. It was coined by Charles Sanders Peirce, originally as Boolean algebra, to describe a streamlined version of the algebra of logic that kind of stripped away some of Boole's initial focus on arithmetic. And then this more abstract form was really championed by Josiah Royce and his students.
Okay.
So, for our deep dive here, to really get what Boole was doing in his own time, we're going to be looking at Boole's algebra, the actual system that he meticulously constructed. You know, the history of ideas, it often involves refinement and people reinterpreting things.
The nuances really do matter. It's not just about the end product, but the journey, the original vision. So we understand the intellectual climate, right? But what about Boole's own drive? Our sources mention his sister, Marianne Boole, and she talks about his lifelong conviction that logic could be brought under the umbrella of mathematical science.
Yes.
And then there's this specific event in 1847 that seems to have sparked a major insight for him.
You know, Marianne's account, it gives us this really valuable glimpse into his thinking. She talks about how he had been chasing this idea practically his whole life.
Yeah.
And the trigger for his big breakthrough in 1847 was this seemingly small public disagreement between, well, his friend De Morgan and the Scottish philosopher Sir William Hamilton.
Okay.
Not the Irish mathematician William Rowan Hamilton, just to be clear. But this debate, it was about quantifying the predicate in logical statements. It seems like it kind of gave Boole the true method, the thing he had been looking for.
Well,
Marianne even said that it really affected him deeply, like a man dazzled with excess of light. And within a few months, he had produced the mathematical analysis of logic. It's amazing to think that a seemingly small academic squabble could spark such a revolutionary idea.
it is amazing. So let's dive into that first major work, the mathematical analysis of logic.
Yes.
For a philosopher trying to wrap their head around his approach, what were his key first moves? How did he start building this bridge between Aristotelian logic and his algebraic language?
Well, right off the bat in LL, Boole shows where he's going by focusing on the symbolic method. He says that whether a logical analysis is valid should depend only on the rules governing the symbols, not on what they specifically represent. That's a very important philosophical stance. He then introduces the symbol 1 to represent the universe, the totality of all possible classes. And drawing from how algebra was being used with differential operators, and really aligning with De Morgan's view of symbols as operations, he brought in elective symbols, lowercase letters like X for class X, Y for class Y, and so on. These weren't just labels, they were representing operations of picking out members of a specific class from the universe. So X is like an instruction. From everything that exists, select the things that are X.
That's a subtle shift, but it's profound. So it's not that X is the class itself, it's the act of picking out that class.
Exactly.
It really highlights the symbol's active role, and when X appears by itself, it's implicitly operating on the universe.
That's right. He clarifies that when you see an elective symbol like X alone, the universe 1 is the implied subject.
Okay.
So X1 is indeed the class X.
That makes sense.
This operator perspective is really fundamental to understanding how he set up his algebra for logic.
Okay, so then how about the basic ways these classes relate to each other? How did he represent things like logical A and D or R and not using these elective symbols in MAL?
The first operation he defines is multiplication, just putting symbols next to each other like loci. Given that we're thinking of them as operators, xli means you first apply y, you pick out members of y from the universe, and then you apply x to what you've got left. You select the members of x from that subset.
Okay.
So xy1, that represents the class of things that are both x and y, what we usually call the intersection.
Right.
Interestingly, in his later laws of thought, he streamlined this a bit, just letting the lowercase letters stand for the classes directly, so xi would still mean their intersection.
Gotcha. So intersection lines up nicely with multiplication. That's a really intuitive connection.
Yeah.
What about the other logical connectives, though? How do they fit into this picture in ML?
Well, in ML, addition comes in mainly through the distributive law, xu plus v equals u plus fifth v. He specifies that u plus v refers to splitting a class into two totally separate, non-overlapping parts, u and v,
Hmm.
This early way of dealing with addition is pretty important. He also includes the commutative law, xy equals yx, and what he calls the index law, xn equals x, which later becomes the idempotent law, by 2 equals x in laws of thought.
Hmm.
These laws form the bedrock of his algebraic system for logic.
Okay, so with these laws, Boole essentially says, all the tools of algebra, we can use those on these logical symbols.
Mhm.
That's a bold claim, bringing all that machinery from algebra into logic.
It was. After stating those distributive, commutative, and index laws, he famously declares that all the processes of common algebra are applicable to the present system. He even adopts De Morgan's principle for inferences. You do equivalent operations on equivalent things, you'll get equivalent results.
Okay.
So he wasn't seeing his algebra of logic as a totally new thing. He saw it as an extension, or maybe a specific interpretation of the algebra of numbers, the familiar one. And that assumption, it really shaped his whole approach.
So this idea of relying on common algebra, that's a key thing for a philosopher to understand. For Boole and his contemporaries, algebra meant the algebra of quantities, of numbers. So he wasn't starting with some abstract algebraic structure. He was grounding his logic in the established rules of arithmetic and its extensions.
Exactly. And while his initial set of those 3 laws for his logic, looking back, they weren't enough to fully justify everything he does in Elmela, but a helpful way to picture his thinking is to imagine him working with ordinary polynomial algebra, but with this extra rule. Any power of an elective symbol, like x, is just equal to x itself, so xn equals x.
Oh, yeah.
Basically, any polynomial equation that works in regular algebra, he considers potentially valid in his algebra of logic, and so are the arguments based on manipulating those equations.
But there's a big caveat here, right? Even though he's using the rules of common algebra, the specific meaning of his symbols within the world of logic, it brings in its own unique constraints and considerations.
Absolutely. For example, if you do an algebraic manipulation like x do equals x, therefore x1 or x equals 0, no, that's fine in common algebra. But in Boole's logic, that conclusion, it represents a disjunction, not a single equation. At its core, Boole's algebra deals with polynomials with integer coefficients and how they behave when the variables can only be 0 or 1. And those values correspond to whether an element is in or out of a specific class.
It's striking, isn't it, how this restriction to 0 and 1, it foreshadows the whole digital age, with computers and binary code at its foundation.
It really does. A lot of the key polynomials Boole worked with, like 1x for not x, xy for x and y, and x plus yxy for x or y, the inclusive kind, all of these, they only ever result in 0 or 1 when x and y themselves are 0 or 1. These are basically the predecessors to what we now call switching functions in computer science.
That's fascinating. And this index law, which later became the idempotent law, xn or by 2 aoS x, what effect did that have on his logical expressions?
It really simplified things. It meant any polynomial with just one elective symbol, say px, could be boiled down to a simple form, ax plus b.
Okay.
Similarly, pxy, 2 variables, could be simplified to axc plus bx plus c plus d. This made manipulating logical expressions a lot more manageable.
And this simplification, it led directly to his expansion theorem, right? That seems to be a crucial tool for analyzing and manipulating logical statements in his system.
Exactly. He realized that that linear form, x plus b, could also be expressed as a combination of x and its complement, 1x, like this, a plus bx plus b1x. This insight led to the one-variable expansion theorem. For any elective function px, it's equivalent to p1x plus p0, 1x. For 2 variables, the theorem does a similar thing, using all 4 basic combinations, xy, x1y, 1xy, and 1x, 1y. He called these product terms constituents, and the coefficients, things like p11 and p00, he called them moduli.
Constituents, they sound like they're breaking down the entire logical space into these mutually exclusive, exhaustive categories, kind of like the areas in a Venn diagram, where each constituent represents a unique way that classes can overlap or not.
That's a really good way to think about it. For any set of variables, the constituents, they have these crucial properties. They're idempotent. Multiplying a constituent by itself gives you the same constituent backling. Their products with each other are always 0 because they're mutually exclusive possibilities, and their sum is always 1 because they cover all the possibilities in the universe. These properties are key to how Boole used them to analyze logic.
So how did Boole use all this algebraic machinery, including this expansion theorem, to represent the basic propositions of Aristotelian logic, the ones like all x are y or some x are not y? How did he get those into his algebra in Mel?
In Malev, in the chapter called Of Expression and Interpretation, he starts by establishing that the class, not X, will be represented by the symbol 1x. That's where we first see algebraic subtraction coming into the system. Then he lays out his primary equations for the Aristotelian categorical propositions. All x or y becomes x equals y. No x or y becomes x, y equals 0. Some x or y becomes v equals y, and some x or not y becomes v equals x1y. And here, the v seems to represent the idea of existence, some.
This V is interesting. It's how he deals with particular propositions, the ones that say something exists in a certain class, and xy equals 0 for no x or y. That's really straightforward.
Yeah.
It's just saying the class is x and y, their intersection is empty.
Right. He also provides secondary expressions for the same propositions. So all x or y could also be x, y, and no x or y could be x, v1, y. And it's worth noting that in MAL, the equation E equals 0, that seems to act like a predicate. It's claiming that the class represented by the expression E is empty, it doesn't exist. The empty class itself, though, it wasn't explicitly given the symbol 0 until his later laws of thought.
Okay, so for Boole, the whole process of doing a syllogism, drawing conclusions from premises, that became a matter of manipulating algebra, specifically using this technique called elimination. The goal was to start with the equations representing the premises, and then eliminate the middle term, the term common to both, to get a new equation. And that represented the logical conclusion.
Exactly. Elimination was a standard tool in the theory of equations, and Boole adapted a pretty simple result for eliminating a variable from two linear equations. So if you had premises about classes x, y, and z, and they can be expressed in the forms a plus b or 0 and psi plus d equals 0, where y is the middle term and a, b, c, d don't involve y, then you could do standard elimination and get add bc equals 0 as your conclusion. That was the heart of how he initially handled syllogisms in MAL.
But our sources mention that this first elimination method wasn't perfect. It couldn't handle all the valid syllogisms. There were some limitations.
Right. Sometimes, especially with premises using those primary equations, like the ones of the form a and psi equals 0, eliminating would just give you 0, 0, even when there was a valid logical conclusion you could get from the premises. That's one reason he introduced those secondary expressions for the categorical propositions. He was hoping those would give him a more solid base for getting all the valid syllogisms. He even suggests in a later footnote that the secondary forms might be better because they're more general and easier to interpret logically.
And he also applied his algebraic approach beyond just the traditional categorical syllogisms. He tackled hypothetical ones too, the ones with if.then or either.or statements.
Yeah, he defined a hypothetical proposition as basically two or more categorical propositions linked by a copula, a connecting word like if or.
Right.
His method was to break those hypothetical propositions down into propositions about classes of cases or conjectures of circumstances. For a categorical proposition X, he would use the symbol X to pick out the cases where X is true. So he's shifting the focus from classes of things to when propositions about those things are true. He's moving towards propositional logic by talking about the truth of statements.
Exactly.
And he would tie an elective expression, often a constituent, to each possible truth value assignment for the propositional variables involved. Say you've got two propositions, X and Y. The case where both are true would be the constituent Y. The case where X is true and Y is false would be X1Y, and so on, for all the possible truth value combinations.
And then a hypothetical proposition, something like X is true or Y is true, could be represented by adding up those constituents that match the cases where it's true.
Precisely. For that inclusive or, the expression would be the sum of the constituents for X true and Y true, which is XY, X true and Y false, which is X1Y, and X false and Y true, which is 1XY. This sum simplifies to X plus Y, XY. Boole would often set this equal to 1, representing all the cases where that or statement is true.
So he's clearly working with truth values and combinations, but he stays mainly in the realm of algebra. He doesn't really go for truth tables the way we do now, as a systematic way to figure out if a complex proposition is true based on the truth of its parts.
Right. His focus was on translating logical premises into equations and then manipulating those equations using his rules. His system could handle any propositional formula. Our source lays out how to do that with that recursive definition of algebra. But it's different from the later axiomatic systems and truth functional stuff that we see in modern propositional logic.
Okay.
He's all about the algebraic connections between these expressions representing conditions or cases.
And beyond just translating Aristotle and hypothetical syllogisms, Boole also developed more general theorems in his algebraic system in ML.
Yeah. Starting in the section on properties of elective functions, he formally lays out his expansion theorem and the properties of those constituents. It's interesting, he even uses power series expansions in his proof of the one-variable expansion theorem. It hints at maybe applying it to rational elective functions, but he doesn't explore that much in MAO. He also introduces division in this context, though that stays a bit tricky, and he mostly drops it in laws of thought.
But his expansion theorem was powerful, right?
Yeah.
It let him say exactly when two elective functions were logically equivalent based on their moduli, those coefficients.
Exactly. Two functions, px and qx, are equivalent in his algebra if and only if their matching moduli are the same. So p1 and p0, q0.
Okay.
And this idea works for functions with more variables too. Plus, he showed that any equation like p equals 0, that's the same as saying all the constituent equations where the modulus isn't 0, those have to be true. This meant that every equation in his system had a logical interpretation.
And he tackled the problem of solving those equations, right? Expressing one class in terms of others, even if it meant adding conditions or constraints.
Right. His solution theorem provided a method for that. It often involved using formal division and then the expansion theorem. Sometimes you'd end up with fractional coefficients, and you had to figure out what those meant back in the language of logic.
Right.
Often this revealed necessary constraints on the other variables. His use of formal division might seem a bit off from a modern algebraic perspective, but it was a key part of how he derived logical consequences.
So it sounds like mathematical analysis of logic, even with its known issues and the areas where he would improve things later, it laid down the foundation for his whole project of representing logic through algebra.
Definitely. ML shows that deep connection Boole saw between his logic and common algebra, especially with the addition of by 2 is x. His methods for elimination and reduction might look basic compared to his later work, but the powerful expansion theorem and the method for solving those equations, they were already there. It really contained the blueprint for the more developed system in laws of thought.
Right. So that brings us to Laws of Thought, his second big work. How did this book build upon the foundation laid in ML?
Well, Laws of Thought, published in 1854, it was Boole's attempt to tidy up and fix some problems he saw in ML.
Okay.
He also wanted to give more concrete applications of his system, notably to probability theory, which is a fascinating topic, but we won't be going into that today. In terms of logic, a big change was explicitly introducing 0 for the empty class, alongside 1 for the universe.
Right.
He also gave a more direct definition of multiplication as representing the intersection of classes.
Okay. And his approach to addition, that seems to have changed quite a bit in Laws of Thought.
It did. It went from a general operation to a partial one, which only works under certain conditions. In LT, x plus y representing union or combining classes is only defined when those classes x and y don't overlap, meaning when their intersection xy equals the empty class, 0. Similarly, subtraction xy only makes sense when y is fully contained in x. This more restricted approach to addition and subtraction came from Boole's commitment to keeping the rules of ordinary algebra intact in his logical system. For instance, if addition was always defined, then x plus y, 2 expands y, if you expand that, would mean xy equals 0, forcing x and y to always be disjoint, which isn't true for all classes.
So sticking to standard algebra, even if it made representing some logical operations trickier, that was a guiding principle for him.
It definitely was. He could define union and other operations like symmetric difference and complement within his partial algebra, which let him turn propositions into equations.
Okay.
But the key point is that addition being partial, needing those disjoint classes, that was central to his system in laws of thought. Even to define the complement, he needed subtraction, which itself was partial.
Now, one of the most interesting things about Laws of Thought, especially from a philosophical point of view, is his rule of 0 and 1. What exactly was that rule?
The rule of 0 and 1, he presents it pretty casually in LT, basically says. Let's imagine an algebra where the variables, x, y, z, and so on, can only be 0 or 1. Then he argues that the basic laws, axioms, and operations of this algebra would be exactly the same as those of his algebra of logic. The only difference is how we interpret the symbols. One way they're classes or propositions, the other way they're just 0 and 1.
Okay.
He's basically suggesting that you can tell if a logical argument is valid by checking if the corresponding equations work when all the variables can only be 0 or 1.
Ah, so it's a way of grounding those abstract algebraic manipulations back in the real world of logic, where things are either true or false, in or out of a class. It's like saying, if the equations work when everything is just 0 or 1, then the logic has to be sound.
Exactly. While his algebra itself itself wasn't limited to only two values. This two-valued interpretation was how he justified using it for logic and interpreting the results. This rule of 0 and 1 became a crucial tool for proving his theorems, like the expansion theorem, and developing his methods in laws of thought.
And he also tackled the problem of those uninterpretables, algebraic expressions that came up, but didn't seem to have a clear meaning in logic. How did he justify those in his system?
He defended using those uninterpretable expressions by comparing them to imaginary numbers in math, specifically in how they're used to derive trigonometric identities.
Right.
He argued that as long as the final results of your manipulations made sense logically and could be proven valid, the steps in between didn't have to have a direct, clear, logical meaning.
Okay.
But our source points out that his justification, which he called principles of symbolical reasoning, it didn't always line up perfectly with the details of his partial algebra and laws of thought, especially with those restricted definitions of addition and subtraction.
And there was that famous disagreement he had with William Stanley Jevons about the logical law x plus x equals x, right?
Yeah.
That highlights a fundamental difference in how they thought about logical OR.
Yeah, that's a really telling debate. Jevons was adamant that if plus O represents logical union, the inclusive OR, then x plus x should logically be just x.
Right, if you have something or itself, you just have that thing.
Right, but Boole totally rejected this law. In his system, if you accept x plus x equals x, you can manipulate it algebraically to get x equals 0, which would mean every class has to be empty. And that was totally against his whole idea of basing logic on regular algebra, where that identity doesn't usually hold. His insistence that addition only worked for disjoint classes, that was the sticking point.
This really shows the tension in what Boole was trying to do, to use the power and rules of algebra while also capturing how logic works. It seems like Jevons wanted a system that mirrored our intuitions about logic more closely, even if it meant breaking some algebraic rules.
Exactly. And that difference in thinking led Jevons, and others later, to develop systems that were closer to modern Boolean algebra, where union is a basic operation that does follow x plus x equals x.
It's amazing how that one little difference in defining OR led to such a big split in logical algebra. And as we talked about earlier, the common idea that Boole's algebra is just Boolean algebra, well, that's not quite right.
Right. Logicians like Theodor Halperin have really helped clarify that Boole's original system, with its strong ties to common algebra and those partial operations, it's different from modern Boolean algebra, even though they both aim to give us an algebraic framework for classes and propositions.
So how did Boole actually put his refined general method from laws of thought into action? What were the steps involved in using his system to solve logical problems?
Okay, so for primary propositions, those are statements about classes, not hypothetical ones. His method in LT had a few set steps. First, you translate the premises into equations using his symbols. For universals, like all x is y, that'd usually be x is y, which you'd often rewrite as xv equals 0, or even more commonly, x is y or xy equals 0.
Okay.
For particulars like sum x is y, you'd use parameters like v or w to represent sum, so you'd get something like vx equals vi.
Those parameters for sum, they seem to carry over from LL.
Right.
And our sources noted that using the same parameter for multiple sum statements could cause problems. Did he address that in Laws of Thought?
He did become more careful in LT, especially in the chapter dedicated to Aristotelian logic, to use distinct parameters like v, w, and so on for different existentials in the same problem. That was important to avoid wrong conclusions.
Right, makes sense.
Once you had your premises as equations, the next step was often reduction, combining those multiple equations into one big equation. One common way was to rearrange each equation so it equaled 0, and then add up the squares of those expressions. The final equation, set equal to 0, would represent all the constraints from the original premises together.
Okay, so you take a bunch of logical statements and you condense them into a single powerful equation. What happened next?
Next, or sometimes as an alternative approach, came elimination. If you wanted to derive a conclusion that only involves some of the original class symbols, you had to get rid of the other ones, the middle terms, from that combined equation. Boole's elimination in LT usually involved treating that combined equation as a polynomial in the variable you want to eliminate. Then he would use algebraic tricks, often relying on the fact that variables could only be 0 or 1 to get an equivalent equation without the eliminated variable. One method was to substitute 0 and 1 in all possible combinations for the variables you're eliminating, then multiply the results together.
That sounds like it could get pretty complex, especially if there are many class symbols in the argument.
It could. Alongside or after elimination came development, our friend the expansion theorem.
Okay.
This meant expanding some of the terms in the combined equation, or the one you got after eliminating, in terms of the constituents of the class symbols. This let Boole see under what logical conditions the equation was true.
And if the goal was to figure out what a particular class is, its logical definition based on the premises.